So hello everyone. Today we'll see process duplication in Linux. How do we do process duplication and how we create child processes. I told you earlier that there is a system called fork which is used to create the child process. Okay. The moment you give fork call, a child process is created such that the child process will have its own identity. The child process will maintain its own task structure, its own PID, its own PPID, its own program counter, and many other attributes of its own. But the child process will not have its own process context. It does not have process context of its own. The child process will share the process context of that of the parent process. When we give the fork call returns -1 or 0 or a positive value. Okay, it returns -1 on error. It returns the positive value, which is the PID of the newly created child process. Okay, fork creates a child process and returns the PID of the child process. How the fork is done? Look at this diagram carefully. When we do the fork, the child process is created. The child process will have parent PID +1 PID if available, otherwise another +1. The PPID of the child process, which is given in child's task structure. The PPID of the child process is the PID of the parent process. I am removing my headphone. If you have to ask me some doubts, you please put in the question mark in the chat. The program counter of the child of the parent process is copied, current program counter value is copied to that of the parent. Now what is this current program counter value? The code segment goes from some logical address, these are assumptions. The code segment goes from logical address 1000 to logical address 2000. Between 1000 to 2000, say at 1400, fork call is given by the parent process. The moment the fork call was given by the parent process, child process was created here at this point. Okay, child process was created here. So the copying, the task of copying things, PID, PPID, program counter, from the parent's task structure to the child's task structure happened here. Okay, happened here at this moment. At this moment, when the copying of the parent's process context to the child's process context happened, at this moment, the program counter value was 1400. So therefore, what is copied from the parent's program counter, the current program counter value 1400, got copied to the program counter of the child process. Child process will execute instructions found at this program counter logical address value. So at this 1400, it will find fork, and rest of the statements from this particular logical address till 2000, rest of the code segment is executed by child also. This was executed by parent and this is executed by child, including the fork statement, because the child starts executing statements from 1400 logical address. In our case, at 1400 it found fork. So therefore, fork system call is executed by child process also. If you see, the return value of fork is 0, executed by child as its first statement. If child executes fork as its first statement, it doesn't go further and doesn't create a grandchild. Instead, it returns 0. So that's an indicator for us that the fork is executed by child or fork is executed by parent. Let's move on. Have a look at this program. I showed this program to you earlier, in which the fork call was given and the return value of fork was either -1 for error or 0 if fork was executed by child, or it was some positive value if executed by parent, and that positive value was nothing but child's PID. So RET could contain anything. RET could contain -1, in which case we will report error. Or if it contains some 0, we will say that the child is executing, we'll print PPID and PID. Or default, which is parent executing, we'll say parent, we will print the PID, PPID, all this stuff. Okay, so let's see how it runs, how this program works. We have seen this how this program works last class. Look at the blue line. These are those statements that are executed by parent. At the switch, parent finds that the RET is some positive value, so it jumps to default. Then from here, rest of the statements are executed by parent. Look at the green portion. This is child's execution thread. Child executes from here to here. Then the RET was found to be 0. Then it jumps to case 0. Execute this portion, skips the parent's portion, and this is a common statement out of switch. So this is executed by both parent and child. We did this program the other day. Here it was. Okay, and then we executed it. Here it was. So both parent and child executed begin, a common statement executed by parent. Parent says RET value is something, and the address of RET is this. And then meanwhile, when parent executes this statement, after that parent goes to 1 second sleep. When the parent goes to 1 second sleep, then the child gets an opportunity to execute. The child prints the value of RET and the address of RET. The child prints value of RET as 0, and the address of RET is same. Address is same means the previous value of RET that was in parent is overwritten by that of child. Then after some time, then the child goes ahead and prints end statement. Then the parent comes out of sleep and parent prints value of RET, which shows here that it is not overwritten at the same address. So which explains to us that the RET was not overwritten. Instead, there were two RETs now. One RET exclusively in the same stack segment, but in a different stack in the same stack segment, whereas the child has the same variable with same name with same logical address, but at different location within the same stack segment but different stack. Then the concept of logical address also I tried to explain it to you there. Okay. So I hope you understand the concept which is called copy and write. This concept is called copy and write concept. COW, cow concept, famously known as cow concept. Okay. We move on from here. In this program, let us do one thing. Let us take a few. This was RET value, which was the return value of fork. Let us take two more variables, int I and n. Both I and n are local variables, so both I and n will go in stack segment. Let the child process initialize the value of n to 10, say 15, and the parent process, I remove the sleep, and this additional print statements I remove now. And parent makes n is equal to 30. Now when I come here and try to print the value of n, can somebody tell me what will be the value of n here? Yeah? Who was that? Anybody else can make a guess? Yes, this answer is correct. Just now I explained you the concept of copy and write. So there will be two n's, one exclusively for the parent and one for the child. Both the n's will have same name, same logical address, but carry different values because it will get different values. When this particular common statement will be executed by parent will refer to its own n, and when it will be executed by child will refer to its own n. Okay, let me show you this. There you see, the n printed by both the processes one by one, and both the processes gave their own values, n30 and n15. Okay, just now I told you about copy and write, isn't it? Okay, let's move on. Remove this print statement now. I am going to start a for loop here. For I is equal to 0 to I less than n I plus plus. Can you tell me this in the chat? Tell me in the chat that this particular for loop will be executed by parent or child or both. Both. Yes, Ashish, you are right. Both is answer is correct. Both one by one answer is not correct. First, the parent is also not correct. Both is correct. So this will be executed by both parent and child. Okay. Both the processes will print their parent PID and PID. Then we put a 1 second sleep here so that it happens with the 1 second delay, so that we are able to see it and do the observation. Otherwise it will be execute so fast that we'll not be able to do any observation. And after that, towards the end, like when the process will come out of for loop, they will print end statement. So now tell me, as you told me just now, that this particular statement will be executed by both parent and child. This particular for loop will be executed by both parent and child. Fair enough, that's correct. Now you please tell me how many times parent process will execute this for loop and how many times child process will execute this for loop. Give the answer in chat. Yes, Swati, your answer is absolutely correct. Child will execute this loop 15 times and parent will execute this loop 30 times. Let's see this. Here you see, both parent and child started executing the loop. Both parent and child processes are executing the same file, same program, executing the same function. After 15 iterations, the child is over. Now only the parent process is executing. sorry, only the parent process executed, and now the parent process is also over. You notice this. Okay, now I'll run this program once again and we'll have to do some observation. ps-ax command will show us the process table, which is a list of all executing programs. Here I check. See, you have two a.outs, 45 for parent and 46 for child. So 45 and 46 both programs, parent and child, executing. Okay, after some iterations, 15 iterations, you will see that the child process is over, only parent is executing. So the child process is over, but 46 is still visible in the process table. If the child process is finished execution, if the child process has terminated, then why is it that child process is still visible in the process table? And what is this Z plus and what is this defunct? Well, what has happened is the child process has finished execution is correct, but the child process has not yet terminated its execution. The session is still not terminated, though the child process has finished execution of all its statement. This state of the program, where the process finishes execution of all the statements but is not terminated, this is called zombie state. This happens between the parent and child in this scenario. Suppose this is the parent process executing. And the parent process here creates a child process. The child process executes and finishes its execution here. At this point. Then from here to here, till the parent process finishes its execution, the child process enter into a special state called zombie state. Okay, and the process lies in the process table. The child process lies in the process table as a defunct process. Defunct process is a process which will never be allocated. With processor. For execution. So now the process will live in the process table fine, but it will never be scheduled. It will never be scheduled by the scheduler and never be allocated with the processor. It will never move to scheduler's run queue. Zombie is that state. Okay. Now, when the parent process finishes its execution at this point, then the parent process will terminate the child process. Okay, when the parent process reaches here, then the parent process terminates the child process. At this point of time, the parent process finishes its execution and gets a free CPU cycle after that. It could be before that also, anywhere. Whenever the parent process gets a free CPU cycle, the parent process will notice that the child is defunct and zombie state. The parent process will terminate the child process. No process in Linux can commit suicide. That okay, I am finished executing all the statements, therefore I go ahead and I commit suicide. No process will do that. A process is always created by some other process. The creating process is called the parent process, and the created process is called the child process. When the child process will finish its execution, it will always be terminated by its parent process. Okay. Now the parent process will terminate the child process by execution of a special code provided by the operating system called termination section of the code. The termination section of the code primarily concentrates on releasing all the resources that were used by this program during execution, destroying the task structure, and if required, the process context and associated memory. But in case of child process, there is no process context. Okay. After that, when the parent process will initiate the termination section of the child process, only then the child process will get terminated. Till then, till that could happen, the parent process is busy executing its own statements and doesn't get a free CPU cycle, it could not execute the termination section of the child process till that moment, till that time. The child process enters into a special state called zombie state, and it lives in the process table as a defunct process. Okay. Deepak says, sir, every child process would go in zombie state after completely execution of child process. That is not necessary. The child process enter into the zombie state only if after finishing the execution of the child process, its parent process is busy executing itself or doing something else. Like in our case, after the child was over, the parent process was busy executing in the for loop, or was busy sleeping. So therefore it had no free CPU cycle. It could not get into the termination section of the child process. Okay, resulting in child becoming a zombie process. Now let me modify this. Whenever you have to say something, you put something in the question mark in the chat. Yeah, who was that? Let's have a look at this program. In this program, we have modified n, made 30 for child, and n for parent is 15. Now this loop will be executed by parent 15 times and child 30 times. So in this case, parent will finish before the child process. This is exactly what Ashish was asking. Yes, Ashish, like I have taken your query and I am resolving it now. So here in this case, in this case, the child process will execute 30 iterations and the parent process will execute 15 iterations. So what will happen is, parent will finish its execution after 15th iteration, print end and parent will go, whereas the child will continue executing till 30 iterations. What happens in this scenario? I'll tell you half of the things. When the parent process finishes execution, then the parent process's termination section also has to be executed. The parent process's termination section will be executed by parent's parent. Now the parent's parent in our case is shell. So there is a program called shell which is executing. The shell created the parent process which was executing till the here. The parent process had created a child process which say continued executing till this point. So in this case we noticed that the parent process got finished its execution before the child process. So at this point here, parent process finishes its execution at this point. The parent process also cannot commit suicide. The parent process has to be terminated by parent's parent. Parent's parent is shell. The shell notices that the child, the parent process has finished execution. So the shell executes the termination section of the parent process and terminates the parent process. Shell, that was parent's parent, executes termination section of parent and terminates it. So the parent is gone. Okay, parent is no longer there. Parent is gone. It was once, it was there, but now it is gone. The parent process was here once, which executed, but now it's gone. Okay, so what happens to the child process? Question comes here. After this point, when the parent process got terminated, after this point, my question comes here. As child continues to execute, till here. The question is, what will be PPID of child? Child is printing its parent PID. After the parent is over, what will be the parent PID? And who will there be a parent now? This child will have parent who was supposed to execute its termination section at this point of time. As the parent is gone, this will be orphan. This process will go into a special state called orphan state. Means it will not have parent. It will not have parent. Then what will it print in its PPID, which is it is printing in every iteration in the for loop? And a bigger question, will this process ever live as zombie, or what will happen and how will it get terminated? We need to see that. So Deepak says shell would be treated as parent for the child process. Well, that's a good guess. Let's see what happens in this case. Here, after 15 iterations, parent will go. Child will continue execution in this for loop till 30 iterations as an orphan process. Well, and what will it print in its PPID? Will it get terminated? Let's see. Both parent and child have started execution. Both will execute for 15 iterations each. After 15 iterations, parent process will finish its execution and will be terminated by parent's parent shell. There you see, the parent process was terminated. Therefore, you were able to see the prompt here because the parent process is gone and is terminated by parent's parent. Now the child process is executing. Child is printing its PID and PPID. Notice the child PID is 71. Earlier, when the child was executing 71, it was printing its PPID 70, PID 71. PID was 70. After the parent process was over, the child process is printing its PID 1637. Now, what is this 1637? Let us see the process table. 1637. There is a system called, there is a program called systemd 1637. In the process tree in Linux, systemd is the great grandparent of all the processes in the machine. It is this process that keeps tab on all the processes running in the system. Whenever it sees that certain process has become orphan, it immediately adopts it. Okay? Immediately adopts it and prevents it from becoming orphan. Okay? Systemd. Okay? It adopts. The orphaned process and becomes its parent when the so-called child process will finish its execution. Then systemd will execute its termination session. And terminate it. You got that? So no process becomes orphan in Linux. This is the great enhancement in Linux for any other process operating system. Deepak says, even though the process is still remaining to execute, then why it should prompt in the middle of execute? Is it for to change parent of child process? No. You saw the prompt in between here because this prompt belonged to the parent process. because the parent process has finished execution and is terminated, and the parent process was the process that was directly on the shell, on the terminal, and the child process was on the parent process. So when the parent process finished execution, it was terminated by the shell. Therefore, you see the prompt on the shell. Let me execute it once again, and I'll show you the process table also this time. Execute. Both parent and child processes executing. ID 83 and 84. Okay. Then after 15 iterations, you will see that the parent will go. Here, the parent is gone. Properly terminated. No zombie, no defunct, nothing. Because the parent shell was always waiting for the parent process to finish execution. So the moment the parent process finished execution, it was immediately terminated by executing its termination section by the parent shell program. Okay. So this is the concept of orphan and adoption in Linux. There is something more. Look at the shell. Shell is hanged. When the parent process finished execution, it gave you prompt. That was fine. You noticed that. But when the child process finished execution, there is no prompt. Because, look at this situation. When the child process became orphan here, at that point, the child process was adopted by system D. And the system D process adopted it. When the child process finished its execution, then the termination section of the child process was executed by the system D, and the child process was properly terminated and removed. System D is great grandparent of all the programs, including shell. System D does not inform shell. Okay. So nobody informs shell that the child process have also been properly terminated. When the shell started the parent process, and the parent process started the child process, at that point of time, shell maintained a hierarchy of programs, processes that got executed, and it maintained a count of number of programs, processes executing in the hierarchy. According to that count, when the parent process started, that count went up to 1. When the parent created a child, the count went up to 2. Then when the parent process terminated, was terminated by shell, this count was reduced back to 1. Now, one process, that is the child process, was executing as orphan and was adopted by the system T and was terminated by system D, but nobody informed the shell. So shell still maintains that there is one program still pending in the hierarchy, which is maybe still executing, and the shell is waiting for that program to finish. Here you see, shell is hanged, waiting for child process. Well, the child process has been terminated by the great grandparent system D, but nobody informed the shell, hence shell is hanged. Okay. Problem. Okay. So this is the concept of orphan, adoption, and zombie in Linux system programming. Okay, and this is a very, very, very common problem which happens in almost every application. So we have to provide a solution to this, which we'll see in the next class. Okay. Meanwhile, if you have any queries, you can ask me now.